Hello everyone, and welcome to this lecture of Advanced Geodynamics, Theory and Modeling. The topic of today's lecture will be about heat diffusion. So last week we started moving from equilibrium to non-equilibrium thermodynamics. For this, we discretized our system into small control volumes. With them stated local thermodynamic equilibrium in each of the volume. Nevertheless, the volumes are able to exchange mass, momentum, and energy. Therefore, we're able to represent a macroscopic variation of, for example, here, a temperature field. So we will resolve gradients. In order to do this, we've introduced conservation laws, and these were two different forms of a conservation law for mass. So you have this form here, which involves the partial derivative of density with regard to time, and that form here, which uses the material derivative of density with regard to time. We've also introduced conservation laws in a more general form for other quantities such as energy and momentum. So again, you have the form here with the partial derivative with regard to time and the divergence of a flux, which may account for diffusion and advection. And here you have a source term. There's also the form here for energy and momentum, which introduces the material derivative. So today we discuss about the heat equation and the process of diffusion. So we are going to use the statements of entropy production and conservation of energy. We'll be looking at the process of heat transfer. Remember the case that we did earlier. We had a universe composed of two systems here with a hot part and a cold part, and the heat had to diffuse in one direction from the hot reservoir to the cold reservoir. This is also similar to a bar here that you're holding in your hand above a candle, and the heat will be basically fluxing towards your fingers, and at some point you will burn your fingers. So before diving into the flux of energy, I want to introduce the third law of thermodynamics. And the third law of thermodynamics states that entropy reaches a value of 0 in the limit where the temperature tends to 0 in unit kelvins. So that's an important statement because this actually bounds the values of temperature. So 0 Kelvin becomes the absolute 0. The temperature cannot be negative in the Kelvin scale. And in other words, temperature will always be positive. This is important to keep in mind for later because we are going to use these properties. So let's start with the derivation of the entropy production in the process of heat diffusion. So we need to use balance laws, and we'll make one for entropy. So let's take this form of the balance law using the form with the material derivative here. So we substitute A basically by entropy S. So QA becomes QS and BQA becomes BQS. So here entropy is not conserved because we have a production term here. We can take the same equation and we construct one for energy. So we replace A by U, QA by QU, and BQA is 0 because energy is conserved. So we have two equations, one for entropy with a non-zero source and one for energy with a 0 source. So let's focus on the entropy balance law, which is written here, and let's recall the first law. So here's a change of internal energy, du is equal to TdS minus PdV. Now, for the time being, we consider a process happening at a constant volume. So we will remove, or we cancel this part of the relationship here, and we solve for ds. So this gives us ds is 1 over t times du. Then we can replace ds dt in this expression by du dt divided by t, coming from this relation here. So we have in this expression the rate of temperature and the divergence of the entropy flux, as well as the source of entropy. So I just reverted the expression such that Qs now stands on the left-hand side of the equation, because we are going to solve for Qs. Now, to make the algebra a bit simpler in the following slides, we multiply everything by t. So we have TQS. Now we've removed the division by t here, and we have a multiplication by t in front of the divergence of Qs. So this does not really matter for the sign of the production, because this term will have to be positive, and t, remember, is always positive. So it doesn't really matter at this stage regarding the production of entropy. So we have this expression, and we are going to use now the energy conservation to substitute rho du dt by minus the divergence of Qu. So our expression becomes TQS is equal minus divergence of Qu plus T divergence of Qs. So we can use now the product rule, because we have a term here which is the multiplication of T times the divergence of Qs. So let's just make the product rule on TQS, and if we expand, it becomes Qs multiplied by gradient T plus T multiplied by divergence Qs. This means we can have an expression for T times divergence Qs. This expression is here, so T divergence Qs becomes this minus that. So we can substitute the T divergence Qs by this expression here, and the entropy production becomes TQS equal to minus divergence Q plus divergence TQS minus QS divergence gradient of T. So we can rearrange this expression. We can put everything that is a divergence inside the same divergence term here. So we have the divergence of TQS minus QU minus QS times gradient T. So now this is already an expression for entropy production, but here we have a term which is a divergence term. So the physical meaning of the divergence term is that it causes the spatial redistribution of a quantity, and in no way it produces entropy here. It's not a production term, because it depends on the coordinate. In a way, this term cannot contribute to the production of entropy, so we can cross it out in the entropy production. So we will neglect this term, but before getting rid of it, we will make a choice here. In fact, there are different ways to cancel out this term, and one way, it is a choice here, I state it. One way to make this term 0 is to state that what is here in the parenthesis is actually 0. So we can say that TQS minus QU is equal to 0. This will make this term vanishing. By making this choice, we also state a proportionality between Qu and Qs. So if we set this term equal to 0, we will get Qs is equal Qu divided by T. This will have important consequences for the remainder. So let's continue with this derivation here. And for the time being, there is no divergence term anymore. There is the term Qs times gradient of T multiplied by -1. And this is a production term here. And we want to focus on this term. Remember the relationship Qs is equal to Qu divided by T. So I can introduce Qu for now. So we have Qu divided by T in this expression. And now I can take the T that was standing on the left-hand side and put it on the right-hand side. So we have the expression Qu divided by T squared times the gradient of temperature times -1. And this whole thing here is the entropy production term. It has to be positive. So let's check the term one by one. We have the minus 1, so this obviously will be a negative contribution. We have T squared. T is positive, and if it's taken to the power 2, it remains positive. Then we have the gradient of T. This can be positive or negative, so there is an ambiguity here, definitely. And here we have Qu. And so far we have no expression for Qu, so everything will depend on what is the expression of Qu. So how to make Qs positive? We can make Qs positive by defining the expression of Qu. There is an ambiguity that comes from gradient T that can be positive or negative. So one way to make Qs positive is to select Qu in a way that is proportional to the gradient of temperature. What about trying to define Qu as -k times gradient of T? So if we do so, the minus sign will cancel out and the gradient T will be taken to the power 2. So let's do it. We substitute Qu by -k gradient T, and indeed the minus sign disappears and gradient T is to the power 2. We have a coefficient here, k, which we've seen already in one of the previous lectures. And we have to define that this is a positive material coefficient. So if we check this, if this coefficient is positive, this has to be positive. T squared is positive, so Qs here is positive. And in fact, it's not a big surprise because the expression that was suggested, Qu equals k minus k gradient T, is the expression of the heat flux from Fourier. So K here is in fact a positive material coefficient, which is the thermal conductivity in watt per meter per Kelvin. And gradient T is the temperature gradient in Kelvin per meters. If you express it in 3 dimensions, it would have 3 components, dt dx, dt dy, and dt dz. It's a vector. So let's make the link with what we've discussed earlier. In one of the exercises we did, we were studying this system or this universe composed of 2 systems next to each other, one hot, one cold, and we had an exchange between the 2 systems. In order to reach thermal equilibrium, we set the exchange rate to be proportional to the temperature difference using a factor k here and the minus sign here. In fact, what we were doing at the time, we were using equilibrium thermodynamics with two containers. We did not define a distance between the two systems. We were just using the temperature difference between the two systems. So there was not really a gradient being defined, or there was a temperature difference between the two systems. What we are doing now, we're going towards non-equilibrium thermodynamics, and now we clearly define a gradient. So we have the gradient of temperature. And this allows us to quantify how the temperature varies within the system. It's a quantification of the variation of temperature with space. So we have very similar expressions here, but now we really have the dimension which is taken into account. And remember, we also define the condition under which the heat transfer was producing entropy, and the expression we ended up was minus Q temperature difference divided by the product of temperature. And this defines the fact that temperature should flow from the hot to the cold container. It's the only way to have a positive entropy production. And this is what we derive today from the non-equilibrium formula. We have the minus sign, Q, the temperature square, and instead of a temperature difference, we have the temperature gradient. So we are really going to have a very good match between the two approaches. So let's summarize a bit what we did so far. We've stated an expression for the conservation of energy. There is 0 here on the right-hand side, and the non-conservation of entropy with a QS term on the right-hand side. In this case here, the entropy production term is K divided by T square, gradient T square. So we have an expression for this. And of course, this comes with the definition of the energy flux, Fourier's heat flux here, and the entropy flux, which is proportional. So the entropy flux is QU divided by T. So this is all what we did, or what we have so far from today's lecture. So it's already a lot, but we do not yet have an expression that allows us to predict how temperature varies with coordinate and time. So we have an expression here for U, an expression for S, so we could predict how U and how S vary in space and time, but we don't really have an expression for temperature. So let's try to derive an expression for the evolution of temperature. So we start from the balance of entropy and the relationships we've derived earlier on. So we have the two fluxes for energy and entropy, and a production term for entropy. So let's combine everything together. We have the S dt times rho is minus QS, minus divergence of entropy flux plus big QS. So we substitute QS. QS is K over T gradient T plus K T square gradient T square. That's the expression of big QS. So we get to this level here where we want to again use the product rule. So let's apply the product rule to this product here, and we get K divided by T times the divergence of gradient T minus K over T square times gradient T square plus this term here, which is the same with a plus sign. So here we've assumed that K is a constant in space. for simplicity. So the plus and minus term here, they cancel. So we end up with an equation which is the rate of entropy times the density is k over T times divergence of gradient T. Divergence of gradient is in fact the Laplacian operator, so we can substitute it by the delta T. And now we should go back to the previous lecture where we define the entropy increment as Cp over T times dt minus alpha divided by rho times dp. So we can do it here. We replace the entropy increment and we get this expression here. Once we have this expression, we now finally have the rate for the temperature. Note that we have a rate for pressure too here. So let's solve for temperature rate here on the left-hand side. So this gives us rho Cp divided by T times dt dt is equal to the right-hand side. We can simplify the 1 over T. This brings factor T to that side of the equation. So what we have now are several terms. We have the rate of temperature times rho C, P, is proportional to the sum of a Laplacian here, and this is the adiabatic heating term, which we've discussed in a previous lecture. For the time being, we said we consider constant pressure case, so we can forget about this term. It will come back in a couple of lectures from now. But what we obtain if we remove this term is simply the equation rho Cp dt dt equals k Laplacian of temperature. And this is the diffusion equation. So we have finally an expression that allows to predict temperature as a function of variation, as a function of time, but also as a function of space. That's the diffusion equation. It can be written like this, or we can expand the Laplacian here under this form. This gives the second derivative of t in each of the dimensions of space with a plus sign. What needs to be stressed here is that we obviously have a partial differential equation. It will predict variation in time and space. And since we have a variation in time, we will need initial conditions. Since we have variations in space, we will also need boundary conditions to solve this equation. So this equation is constructed on the fact that the energy is conserved and that entropy is produced. So if we solve this equation, we should automatically satisfy these two principles, and we will do it in the exercise associated to this lecture. With this equation, you can already do a lot of things. I mean, this is part of all mantle convection and lithosphere dynamics simulation code, for example. You can use this equation to predict the thermal structure of the lithosphere in oceanic and continental domains. You can use this equation to predict how diffusion or heat diffuses away from a magmatic intrusion, and, for example, predict how contact metamorphism is evolving with time and space. Or you can use this equation when you're doing calculation for geothermics, if you want to understand how the temperature evolves inside the Earth and responds to pumping of fluids or injection of fluids. So it's a very powerful equation, and the aim of today's lecture was to show you that this equation can be derived from basic principles, and that involves knowledge of what we did in the equilibrium thermodynamics and the difference balance and conservation law we've introduced last week. This process of heat diffusion actually is a source of entropy production, and it's in agreement with the definition of Fourier's heat flux, which was made a couple of 100 years ago already. So thanks a lot for your attention.